All right, why don't we go ahead and get started now? Turned off our lobby music there. My name is Stacey, and welcome to this QGIS 101 webinar. I'll be doing this as a webinar because it's a little easier with the number of people that might be here. We'll have other folks in the webinar soon to handle questions and answers, and I'll stop briefly periodically for questions and answers. A quick overview of what we're going to do today. I'm going to introduce spatial data, the basics of spatial data, the very basics of spatial data, using a software application called QGIS. It used to be called Quantum GIS, shortened to QGIS. QGIS is a great desktop software application. It runs on virtually any operating system. You can run it on Mac, Windows, Linux. There's even a version for Android at this point. So it's very friendly in terms of whatever computing equipment you have, so that you can access the power of GIS applications. One thing to remember about QGIS, though, is that it's a community-created application. There are companies that are behind some of the development of QGIS, but in general, it is developed, created, and maintained by a community of developers and users. And that's been the story for QGIS for over a decade, I think. So that means that occasionally there are bugs, and sometimes things don't work quite the way you would expect them to, but there are usually ways to get around that. And so as we go through the workshop materials today, you may see me have errors, and I'll sort of hem and haw for a little while, but then I'll try and work around those errors. Sometimes things have to do with projections that aren't handled well in particular processing tools. Sometimes it's just a glitch in the current version of QGIS. As a user, if you find these problems preventing you from getting work done, you can always go to the QGIS GitHub repo and put in an issue on any of the problems that you're having with QGIS in general. So a little overview of the materials for this afternoon. Hopefully everyone can see my shared screen here. And I've got a link there to the slides.com slides. That'll be a live version of the slides that I'll be going through here in just a minute. The workshop materials are available on GitHub. I like to put them on GitHub because if people go through them and find issues with them, they can go and put an issue on the GitHub repo, or they can fork the repo, fix it, and then do a pull request, whatever you like to do there. But you'll also find that my name right there has been changed to the URL of the GitHub repo. So at any moment in the webinar this morning, if you find yourself unable to find the materials, that's it right there. And my name is Stacey. I guess I should introduce myself. I'm Stacey Maples, and I'm now the Assistant Director of Geospatial Collections and Services here at Stanford University Libraries. I'm also the head of the Stanford Geospatial Center, and our mission is to promote and support the use of geospatial technologies, data, and software in research and teaching here at Stanford, whatever that means at any given time. The other thing I like to do is open things up to the public. A lot of folks know that I'm very open source minded. I myself consider myself open source. A lot of my instruction materials are online, and in that GitHub repo, you'll find more than just QGIS 101. So this webinar is intended to be a webinar for those folks who have no experience whatsoever with GIS software, with spatial data. So we're going to start with basic principles, and I'm going to start with everybody's favorite, a short presentation. And this is just my standard spatial data intro, and it just sort of gives you a brief overview of the nature of spatial data. Now, Geographic Information Systems, GIS, are actually everywhere. They're in your car. now because we have smart cars that have navigation systems in them. They're in your iPad. There's most certainly in your mobile phone when you use Google Maps or any other applications that ask to use your location. Spatial data is being created and leveraged in those applications, whether it's for the services being provided to you or to mine data about your behaviors is another story, but spatial data is literally everywhere now. And I would argue that essentially all data is spatial, and that's because everything is somewhere, and those locations can be captured and associated with the information that we're gathering in the field. Our own Marguerite shuttle here at Stanford has GIS sort of baked into it. It has GPS units in the buses, and we have a live bus map that shows you where our Marguerite shuttle is at any given time on campus with little moving icons that are moving in the map, so you can see whether or not you need to run or you can walk at a leisurely pace to the bus stop. And that's all happening through GPS, Global Positioning System, being implemented in the bus, and that data being sent over the cellular network to a server that then turns that information about where the bus is into spatial data, probably GeoJSON, so it can be presented live in a map. It's been a while since I changed this slide, but this is an example of GIS that everyone has seen. About every 4 years, every 2 years actually, we sit through elections, and most of our news channels look like this. They have maps with generally 2 colors, which is, arguable whether that's correct or not. And this is essentially a database that has 3 or 4 variables in it. It's got the state abbreviation, it's got the number of electoral votes, it's got the name of the person, maybe, but that's really not even necessary. And it's got a variable, a binary variable, basically that's red or blue. And throughout the night, commentators are going through and they're changing the value of red or blue on that database, which is changing the illustration in the map, as well as aggregating that data into the totals that you see at the top. It's a very simple GIS. Most of the code in this GIS is probably just to make it look nice for TV. So what is GIS fundamentally? Well, the easiest way to talk about this is to talk about going to dinner. When I first started doing GIS, nobody knew what GIS was. There was no Google Maps. There was barely MapQuest. Remember MapQuest? You could print out 16 pages of directions. So the easiest way to talk about what GIS fundamentally is to talk about an experience everybody's had, and that's going out to eat. You go out to eat, you're sitting at your table with your party, you've ordered appetizers and drinks, and the waitstaff comes to your table and takes your entree order. And after they do that, they go back to the bar, right? And there's a computer screen there, and they touch a location that represents your table in the restaurant on the screen of that computer, and then they enter the data that they've collected from you at your table. That fundamentally is a geographic information system. It's taking information that's been collected and organizing it explicitly based upon the location that that data was collected at. And that allows that wait staff and other people on the staff of the restaurant to access that information based on the location. They can touch that table and see how many people in your party have ordered drinks. They can calculate how many people are in the party so that they can decide whether or not to grant the ticket or not, and so on. And so that's really all GIS does. It's a database system that takes data and associates it with the location that it's gathered at. So GIS models the world in a unique way. It takes layers of like phenomena and features and organizes them into data layers, basically. And GIS organizes the world into layers of like features and phenomena. You can see here in this image, I've got a stack of data sets that include, for instance, elevation, satellite imagery, orthophotography, climate data, demographics, hydrology, some sort of sample points, road networks, and so on. And all of these layers can be stacked up against one another. And what that allows you to do when you co-locate all of that data against one another, it allows you to analyze across those layers in geographic space. So we could take two layers of data, for instance. We could take climate data, temperature, and elevation data, and co-locate them with one another in geographic space, and then sample across those two data sets in the same exact places, and then produce an analysis from those sample points. And in this case, just a simple regression analysis on the relationship between elevation and temperature. So we use a couple of different data models generally in a geographic information system or in geographic software or software packages that handle spatial data. And for the most part, we're dealing with two major models: the vector data model, which is points, lines, polygons, and then the attributes or the information about those locations that the points, lines, and polygons are modeling. Raster data is completely different. It's pixel-based data. It's like the imagery that you create when you take a photo with your phone. And it generally is made up of a single attribute when you create a raster data set, something like elevation or the distance from one set of features to everywhere else on the Earth. So let's start with raster data because it's actually the most familiar data to most people. Raster data is pixel-based data. When you take an image, create an image with your phone, you're actually creating a raster data set. Actually, you're creating three raster data sets, one in the red, green, and blue part of the spectrum, and that's being reassembled into this millions of color image that you see on your phone when you look at the photo that you just took. Now, in spatial data, what we're concerned with is the value of the pixels in these data sets. And so pixels, when you zoom into one of those images you create and see the squares of color in that image, those are pixels, and they're actually just numeric values to the computer. An image is an array, an XY array of numeric values that a computer can turn into an image of you or your lunch or the elevation in a particular part of the world or the temperature in your neighborhood. Again, those pixels are numeric values. Here they represent elevation. And one of the values of raster data and raster data in spatial software in particular is that you can visualize this data. So I can't look at this array of numbers and quickly see a pattern, right? I have some nephews that can do that. I think one of my kids could probably do that, but I can't immediately see where there's peaks in this data set and where there are valleys. But if I apply what's called a color ramp to this data set, I visualize this data set in a geographic information system, I can immediately see that we have peaks here and here and here, and that there is a valley running right diagonal down the center of this particular area. Again, imagery is a form of raster data. Here you see a satellite image, and this is an unusual image because everything in it looks bright blue or red. And that's because what we've done here is we've tricked nature. The satellites that we use to image the surface of the Earth can see outside of the part of the visible spectrum that our eyes can see in. And most commonly, we collect something called infrared. And that's a band of data like the red, green, and blue that your phone collects that gives us information about the surface of the Earth. Here in this image, you see that there are some deep red areas in the image, and those areas are healthy vegetation. And what's going on there is we've taken the RGB model that's used by our computers to show us images with millions of colors, and we've replaced the red part of that RGB model with our infrared layer. And then we've put our red in the green and our green in the blue, and we've kind of thrown away blue because for lots of reasons, blue is sometimes not very useful to us. And what we end up with is this strange image, which is actually quite useful because you can see in the image, healthy vegetation is very dark red, right? Because healthy vegetation reflects very highly in the infrared part of the spectrum. You can see that urban built up areas tend to be almost white, completely saturated across those three bands of data. And that's because things that we build tend to reflect very highly across the spectrum. You can see this streak of dark area here down diagonally through the image, and that's a river. That's water. Water tends to absorb very highly across the spectrum, and so in fact you have very low values, and so it appears very dark. And all of these things, what they are they're building up a spectral curve of objects on the surface of the Earth. We know how vegetation reacts in the infrared, the red, the green, and the blue. And so we can identify these things on the surface of the Earth, and we can tell things about the surface of the Earth from images of this type. We'll expand on that in just a minute. Vector data is a completely different type of data. It's points, lines, and polygons. Points are defined by a single coordinate pair. In this case, 0, 0 is actually a beloved location in the world of geospatial data. It's referred to as Null Island. If you look at it, it's just off the coast of Africa. And if you look in Google Earth, there's actually some data. There's sort of this idiosyncratic data error mountain right at the 0, 0 point on the lat longs there. And that's an artifact of old soundings that had null data or poorly placed data points. And so it's created this sort of data volcano right there that you can actually see in data sets. You can connect 2 points to create a line. You can see that here, and then you can close that line to create polygons that enclose areas. The real power of vector data is that you can associate an almost infinite number of attributes with vector data. Here you see we've got census blocks represented as on a color ramp based on population, raw population, which by the way is a terrible idea. I should change that slide. But with each of those census blocks, we can associate an almost infinite number of attributes with each of those census blocks. And if you've ever looked at census data, you know this to be the case. There are literally thousands of tabulations and crosstabs within the census data sets. Now, these two data formats are not mutually exclusive. In general, we use the vector data format, the vector data model, to model things that have discrete dimension that can be said to be possibly plural, things like houses or streets or locations of fire hydrants or the area of burn of a particular fire and so on. And raster data is generally used to model things that vary continuously, things like temperature or distance from something to everywhere else, or elevation and so on. But that's not always the case. They are interchangeable. And one of the things that you have to remember about this is that interchangeability can be useful sometimes, but it can also be costly. And what I mean by that is, for instance, you can see here in this image, we're modeling the locations of hotels. You can model them using vector data on the XY grid, right? Or you can model them using raster data. But with raster data, you have to account for every location. You have to account for every raster cell. So you not only have to tell the raster data set where the hotels are, but you also have to have a value for every location that hotels are not. This means that discrete data of this type is more easily and more efficiently stored in the vector data model. And that's because with vector data, you really only have to model where things are using coordinates, and you don't have to account for all of that empty space in any way. Now, on the flip side, we can use the vector data model to model things and visualize things like that are often modeled as raster data. And probably the most familiar way of doing that is taking elevation data, which is traditionally stored in a raster data format, at least digitally in the GIS world. And we can use what are called contour lines. And everybody's familiar with these. You can switch in Google Maps to the elevation view in Google Maps, or if you've ever seen a USGS topo map, you've seen these lines of constant elevation, contour lines. That's simply a vector representation of elevation data, a continuous variable. All right, just briefly, we're going to talk about coordinate systems. And in fact, we'll talk in the workshop a little more about coordinate systems, but we're going to just skirt over them a little bit. And what I'd like to say about coordinate systems, the most important thing to say about coordinate systems is that there are two types that we deal with in spatial data. There are geographic coordinate systems, and those are the coordinate systems that locate things on the actual oblate spheroid, that right there, the three-dimensional shape of the Earth. And these are traditional latitude and longitude coordinates that you're used to seeing on a globe, on a three-dimensional representation of the Earth. But it's very difficult to represent that curved Earth, especially for very large regions, on a flat surface. And that includes computer screens, not just paper. And so the way that we manage that is to project the three-dimensional spherical or oblate spheroid that is the Earth onto a flat surface. And we do that by means of mathematical transformations of the geographic coordinates to a flat plane. That transformation is called a projection, and there are lots of different kinds of projections. And in general, for large regions, a projection is designed to preserve something about geographic space. That something might be distance, it might be direction, it might be area, it might be the shape of features, and so on. But in general, projections are only really good at preserving one thing about geographic space, unless they are limited to a very, very small area. So for instance, in the United States, we have this system called the state plane coordinate system. And if you are working completely within a state plane zone, which tends to be very small, about the size of the state of Connecticut, you can ignore the distortions in most of your measurements when you use the state plane coordinate system. But in general, if you're not working with that type of a very large-scale coordinate system, in general, you need to select your projections based upon what it is you're interested in measuring. And we'll talk more about that in the actual workshop. All right, how is GIS data created? Well, it used to be we'd go out into the field and create data with GPS units. We still do that. We still do field work. We still do archaeology. Folks still go out into the field with tablets now that are GPS enabled and do surveys and collect spatial data associated with that. Anymore, because we live in an app-based world now, we can actually use our cell phones to collect data. Virtually everyone has Google Maps on their phone. You can mark locations, you can mark where you parked. Sometimes Google Maps will actually mark where you parked for you, so it makes it easier to get back to that location. But there are hundreds of spatial data apps that are available for Android, iOS, Windows Mobile, and many of those are capable of collecting very complex and very accurate spatial data. The GPS units that we used to use in the field would have an accuracy of about 3 meters. And that's the same accuracy essentially as your iPhone. Collecting all of that data and aggregating it, we can aggregate, the collection of data by many different people into databases. This is an example of a database for a tree survey that I ran for years in New Haven, Connecticut. We can also create spatial data from existing data formats that are obsolete or don't play well with our spatial data software that we want to use. Paper, for instance, is notoriously difficult to jam into a computer program. And so what we generally do is we scan the images of a paper map, and we do what's called georeferencing. And in this image, you see we've got a map of California, and we've identified points of coincidence in the map of California, as well as a reference map of California. And using that technique, we can actually create an image that's sort of geospatially smart, so that when we bring it into a GIS application, it knows where it belongs on the geography. And we can then extract data from that particular map. So in this case, this is an application that the New York Public Library deployed years ago that allows you to digitize and correct the machine digitized building footprints from Sanborn fire insurance maps, which is a really, really cool map collection. You should check that out, the Sanborn fire insurance maps. After the webinar, Google it. We also collect data increasingly with satellites, and this is both in the public sphere as well as the private sphere. There are companies now that are putting up microsatellite constellations that are capable of imaging the Earth multiple times a day. Here at Stanford, we subscribe to a service called Planet.com. Planet.com has a constellation of hundreds of satellites that orbit the Earth on a polar orbit in such a way that they can image the entire Earth at 3-meter pixel size every day. That's incredibly powerful because when you have that kind of cadence on your satellite imagery, you can see very high resolution change on the surface of the Earth. You can see things like flooding. You can see things like deforestation. You can see things like the capacity of ports and so on. Now, with satellite images, again, revisiting this idea that a satellite can see outside of the visible spectrum, see things that we can't see with our naked eye, you can produce images like this. This is an image of New Haven, Connecticut. You can see that it's a false color infrared image like we discussed before, where we've thrown away the blue, shifted everything down, and put the infrared into the red so that the tree canopy and grass cover of the city is very distinct. And you can see that the water is also very distinct. And you can also see things like here in the sports complex, you can see that the football stadium has grass, but the soccer stadium has turf. If this was a true color image, we wouldn't be able to see the difference between those things. Now, a computer can see even more differences, more fine-grained differences. And so we can use what's called the spectral curve of targets that we're particularly interested in, things like transportation, water, building footprints, canopy and grass and bare earth. We can have a computer program classify every pixel in this particular image into its component parts. And then we end up with a data set like this. Now, this is a completely different data set, right? This is a data set that has, I believe, 7 different values. 0 through 6 are the values in this raster data set. And each of those numeric values represents a class of ground cover. And this is a 1-meter resolution land cover data set. It's very useful for measuring things like tree canopy cover and so on. And then, of course, spatial data, as I mentioned before, is being created constantly by us. If you're using Google Maps to navigate somewhere, and you've got the traffic turned on so that you can see, how long this traffic jam that you just hit is going to take you to get beyond so that you can get on your merry way, you should also know that every time your phone sends a request to Google to ask for the new part of the map that you've driven onto, you're sending a lat-long coordinate because it needs that information to send you the correct part of the map, right? Well, that lat-long coordinate is being aggregated with all the hundreds of thousands of people around you who are also driving somewhere. And that aggregated data is what's producing the traffic data that you're looking at. So you're literally being fed back the data that you're producing as you drive across the surface of the Earth. So what does all this enable? What does this allow us to do? It actually allows us to do a lot of really cool things. Some of them we haven't even thought up yet. And this is the really exciting thing about spatial data and spatial data technology, software and hardware that goes along with this, this area of interest. We really are just now scratching the surface about what we can do with spatial data sets of this type. But some really useful things that we can do are things like this. We can take an historical data set, and we'll actually do this in the workshop today, and we can turn it into a more modern version of itself. So here we have a scanned image of John Snow's cholera map from 1854. If we take that and we lay it on top of modern geography using a process called georeferencing, then we can digitize the data that's in this map about this outbreak, this cholera outbreak, into a modern spatial data format that allows us to subject it to all sorts of analyses. And that's exactly what we're going to do today in our workshop. You can take data sets that are not explicitly spatial yet, and you can turn them into explicitly spatial data sets. Here's a data set that I obtained years and years ago as a spreadsheet, and it had the zip codes in every record to identify the location that each of these records was associated with. So I simply ran that through what's called a geocoding service. And that geocoding service took every record and associated a lat-long coordinate with the center of the area that represents the zip code that that record actually had in it. Now, one of the problems with that is I had stacks of zip codes, right? And so one of the powerful things that you can do with GIS is create data that doesn't exist. You can create entities, spatial entities that don't exist, like this equal area hexagonal grid. You can superimpose that across the United States and then count the number of points within each of those grid cells and create for yourself a density map of whatever this thing happens to be. And this happens to be professional party clowns in the United States. And I like to use this because right about this point, people are falling asleep. And so it's a great way to wake folks up, but it's also a great illustration of something that I say all the time. Everything is somewhere, and that somewhere matters. You can geocode, you can map almost anything that you can associate with a location. And then you can take that data and analyze it against other data sets. Once again, here's our example from New Haven, the satellite image that we've classified into the classes of land cover that we're interested in. We can take that a step further. We can actually superimpose neighborhoods onto the entire city. And then we can measure, for instance, the number of pixels. And because we know that they're 1 meter by 1 meter, therefore the total area of things like tree canopy. And when we do that, when we map things like the total area of tree canopy in these neighborhoods, we can see things in the data like this. What is going on in Long Wharf? Why does Long Wharf have such a low number for the tree canopy in this neighborhood? And so that's a research question. We can go and investigate this research question. And there are a lot of reasons behind why Long Wharf is like that. Probably one of the most influential is that during the 70s and 80s, when they were building public housing projects in this neighborhood, they were paying the people who put cement down for parking lots and sidewalks. They were paying them by the cubic yard. For every cubic yard of cement that they put down in these neighborhoods, they made money. They weren't paying them by the job, which would have been smarter because it would have been tied to the volume of the cement. But when you go into this neighborhood now, there are literally no green median spaces to plant anything. So there are organizations now like the Urban Resource Initiative in New Haven, Connecticut, that are going through this neighborhood and actually cutting planting locations into the cement and remediating this problem that this neighborhood doesn't have an effective tree canopy. Tree canopies are great for all kinds of things, remediating stormwater, keeping areas cool, reducing energy consumption in summer and things of that sort. You can model things that just simply can't be modeled in any other way. This is a professor, Jim Scott, who was interested in the reach of the state. And he was particularly interested in how topography affects that reach of the state. And so what he asked was, is there a way to do this with maps? And in fact, there is. We took an elevation data set that represents the elevation in this area of Myanmar that he's interested in. As pixels, as 90-meter pixels that contain the value of the elevation at that point on the surface of the Earth. We used something called map algebra to turn that into a slope map so that we looked at every pixel and its neighboring pixels and we calculated the predominant slope of that central pixel and then gave it that value. And then once you have that predominant slope value as a data set, you can then do something like this, again with map algebra. But what we do in this case is we take an algebraic expression And we plug that map algebra, we plug the slope map into this expression to calculate the time it takes someone to walk across a pixel in this area based on the elevation. And you can see here, we've got 1, 2, and 3 day walking times. And you can see that there is some constriction here, but you really don't see the constriction, and this is the real value, until you superimpose that on a 1, 2, and 3 day walking time on a flat plane. And then you can really see how topography affects human movement across the landscape. Finally, you can see things that you've never seen before in a data set. You could be looking at a data set for years and never notice a pattern in the data set that immediately shows up when you visualize it. This is a data set of photographs that were taken by the US government in the 1930s and 40s. And I worked with this data set for years before I actually plotted it on a map. In fact, the work was to geocode it so it could be plotted on a map. And as soon as I plotted it on a map, I noticed this pattern. If you facet to Jack Delano's photographs, you see this line running along here. And of course, from Chicago to LA, my immediate assumption for the next couple of months was, oh, this is Route 66. He's driving down Route 66 and taking photos. And it wasn't until we laid this data on top of another map, on top of another data set, that I realized, oh, that can't be Route 66, because here's Route 66 running along right here. And there's my data set. And so that finally made me dig into the data to find out what exactly this is. And it turns out this was a study of life along the railroads. Jack Delano took a rail trip from Chicago to LA and took photos along the rail line as he traveled. And that is a sub collection within a larger collection of photos that is of unique interest to researchers. All right, this is my final little thing. Yolda Rosnay in the 70s was sort of lamenting the fact that we had these tools like the microscope to examine the infinitely small and the telescope to examine the infinitely great, but we didn't yet have a tool, which we did by that time in 76, about it was invented, GIS was invented. But he was lamenting the fact that we didn't have this thing that he called the macroscope, that we could sort of turn on ourselves and examine the infinite complexity that is society and its interaction with nature. And GIS is that macroscope. It allows us to take the world and our relationship with it and ourselves and sort of onion skin and pull things apart and reduce them to features and phenomena that we're interested in examining the relationship with, and then do that based on co-location. There's really no more powerful way to take two things that may be seemingly unrelated and find a way to relate them to one another in such a way that you can actually examine the relationship between those two variables. All right, that's all I'm going to do for the presentation for today. The next thing I want you to do is go actually to the GitHub repo. And as I said before, here in the GitHub repo, here in my video, you can't see it right now, so let me stop sharing really quickly. And I'll take a look and see. Excellent. All right, y'all are in. So you have the link to the GitHub repo in the slides. It's also in my video as my name there. So if you have trouble finding it, or you lose the page, or you've come in after we shared the links, you can go straight to my repo there. Let me put it in the chat real quick, and then we can move right along. And that would be useful if I sent it to everyone. All right, there's the slides, and That's it. All right. So we're going to move right along. And the next thing I need to do is actually reshare my screen. We're going to head back to QGIS. All right, hopefully everyone can see my QGIS is the macroscope slide there. One thing I want to point out is that I've put the links to, let's just bring that back up real quick. There we go. QGIS. So you'll see on the repo that this is actually the tutorial with the images and everything here. And I put a number of links at the top. Let me just highlight these very quickly. The first links are links to the Stanford Geospatial Center for getting support on the use of geospatial data. You're welcome as one of the public to get in touch with us as well. We love helping everybody with GIS data. Here you can find our Slack channel. This is our listserv, which is actually a public listserv. Anyone can sign up for that. You can watch for our webinars and announcements about events and so on. This is the link for the QGIS software. And here's the help for QGIS. My tutorial for this particular webinar is at this link on GitHub. And then these slides that I just went through, you can link to here. And then if you're not familiar with the story of John Snow's cholera map, Stephen Johnson wrote a book called The Ghost Map a couple of years ago, which is a fantastic read. You can do it in like 2 nights, 2 evenings, about this event in the 1850s in London, which really had a lot to do with the infrastructure that made metropolitan living possible. This is a great talk about this map that we're going to be working with in the webinar. So if you're so inclined, go ahead and check that out. So hopefully you've installed QGIS. We're not going to install QGIS in this workshop. We're only going to do setup insofar as we need to as we work through the workshop. And the data set I've already downloaded. So at most what I'll do is I'll show you how to unzip the data set. I'm working on a Mac, but remember QGIS works on Windows, Linux, Android. That said, there may be some differences between what you see in my screen and what you see on your screen, for instance, if you're using Windows or you're on a Linux machine. So just keep that in mind. Things might be in slightly different places. They should be called the same thing and so on. All right. The data set that we've got to work with today has a couple of data sets in it. It's got a death address as CSV. This is a comma separated value file, and this actually contains the lat-long coordinates of every address that had deaths in this cholera outbreak in it, as well as the number of deaths at that address. And then we've got this PNG. It's actually just a PNG, not a TIFF. I need to correct that. We've got this PNG, which is just a dumb scanned image of John Snow's cholera map. We're going to georeference that map, and then we're going to digitize the water pump locations from that map. And then we've got this study area.shp. This is a shape file, and it's just a box that describes the area that we're interested in. It's essentially a box around John Snow's cholera map. And we can use this to zoom very quickly into areas that the area that we're interested in. But we can also use it to control the behavior of some of the geoprocessing tools. And then I've got some additional files here, and these files are provided in order to allow you to keep up if you have problems in the workshop. So if you have issues with the georeferencing the map, then you can just add this snow cholera map modified.tiff to your map, and it should show up in the right place. If you fall behind and can't keep up to digitize the water pumps as we go along, well, then you can just add the water pumps.geojson that I've got here. So now what I'm going to do is I'm going to minimize this window, and I've got a copy of a script up here that I'll work from, but I won't return to that document anymore. I'm just going to sort of walk through each of the component parts of that document and talk about them a little bit and then execute them. And so here we're starting with QGIS. This is the long-term release, the LTR. that I just recently downloaded and installed. And I've got, you can see I've got a clean profile, and I created this clean profile so that I have to do everything. I have to set up all of my plugins and all of that for you so that you'll see those things as I do those things. And note that you can always create new profiles. You can make multiple profiles that have different sort of layouts and plugin settings and things of that sort if you need to. I mostly use this so I can quickly get a clean copy of QGIS to show people how to set it up from scratch. And so this is the QGIS interface here. The first thing I want to talk about is just the basics of this interface. And you'll see some images in the tutorial that have this labeled. But when you first open QGIS, what you'll have is these panels. This is your browser panel here. And this is, essentially like your Finder or your Windows File Explorer. You can go to locations on your hard drive. You can mark favorites that, for instance, if you keep a data folder, you can mark it as a favorite and always have it there ready to use when you're using QGIS. And then down here, you have this layers panel, and this is where your data sets will show up as layers. And one thing that's important to understand about data sets in QGIS is that you don't actually add data to QGIS. What you add to QGIS is a layer, and that layer contains a link to where that data lives, because you might be connecting to web services or a data set that's terabytes in size or something crazy like that, and you can't really add that to a document. And the other thing that the layer contains is instructions about how to visualize that data, or how much of the data you want to work with. So you can create SQL queries that turn a data set into a subset of itself. And you can create visualizations in your map, which we'll get to in just a moment. Now, I'm going to go ahead and click New because I want to start with a new map. And so what we see here is nothing. We've got nothing in our map right now. And this area is referred to as the canvas, the map canvas. And this is where the visualizations of all of our data will begin to show up as we add data sets. And so one of the first things that I want to show you is I like to, because I'm an ArcMap user, an old ArcMap user, I like to rearrange the toolbars on QGIS when I open a clean profile. And one of the things that's real handy is you can just grab these toolbars by the handle, and you can slam them right into the side of the interface there and put them where you want them. I'll grab the attributes tools here and put them down there as well. And then I like to clean this up a little bit by only having one bar up here. I can move all of these. And so you get the idea. Your panels, like your browser panel and other panels, work essentially the same way. You can drag them around and rearrange the interface so that you have it the way you want it. All right, in the tutorial, there's a list of each of the toolbars. I'm going to go through them as I use them and explain what they do. And so the first one that we want to use, actually, we can't use any of them right now, actually, because we don't have any data in here. And so the first thing we want to do is add a plugin. And we're going to add the most useful plugin that I've ever come across in QGIS. It's always the first plugin I add. And so if you go to the main menu up here and select Manage and Install Plugins, you'll get this interface where you can search hundreds of user contributed plugins. And so I'm just going to search for Quick Map. And if I spell it correctly, it should come up. There we go. Quick Map Services. This is the plugin that I install first every time I install QGIS. So I'm going to go ahead and select Install Plugin. And what this plugin does is it adds hundreds of web-based map services that you can import to a map and just live stream base map services in your maps. And so I've added this now. You can see, if the plugin is upgraded later on, I can upgrade it and so on. I'm just going to close it. And what it's done is it's added a menu up here at the top of QGIS. And you can see I've got this web quick map services, and I have a few map services by default. I could add OSM, Landsat, but here's a little secret. If you go into the settings for quick map services and you go to more services, you can click on Get Contributed Pack, and that will go and download metadata, I think an XML file, into the plugin. And if I close that, save it, and return to Quick Map Services, I can see now I have many, many more base map services here. And I'm actually going to add Stamens toner light. I like toner light a lot. It's got this nice grayscale. It kind of stays out of the way. If your operational layers, if you're using colors, it kind of highlights your operational layers and keeps the geographic context there without being, you know, sort of dominant in the cartography. It's a great base map to use for stuff like this. All right, I've made changes to my map document, and so I'm going to go ahead and click save. One thing to remember about, and just one second, I'm going to cough. One important thing to remember about most GIS desktop software is for some reason, there's no autosave. I don't know what their deal with autosave is, but you have to be the autosave, right? And so I'm going to go ahead and save this. And I've been working from downloads, and there's my QGIS run through. I'm going to save this as snow map. And this will save as a QGIS project file. So we'll just save that. And if I return to my Finder, we'll see I've got in my folder that I saved that to now, I've got the snowmap.qgc, but I don't have any other data in my map. And that's where this zip file, this QGIS 101 master.zip comes from. You have a link to that in the tutorial right at the top. You should be able to click directly on it and download it. I'm simply going to extract it here in my Mac window and open up this data folder to show you what we've got there. Actually, I'll browse in so it's a little cleaner. Here's our death addresses data set. And here's a style file that for some reason I put in here at some point. Here's our snowmap.png. This is, again, just a sort of dumb image of Jon Snow's map of, and let me pull it down here so you can see it, map of the cholera outbreak of 1854. If we zoom into an area, then we should be able to see the central area. These tick marks represent the number of deaths at each address, and the water pumps are also here in the map, and we'll digitize those into data later on. And then you've got this crazy set of files here that all have the same name, but different prefixes. And these all taken together are what are referred to as a shapefile. Shapefile is a terrible name for this data format because a shapefile is in fact not a file, it's a collection of files. And if you don't have most of these files, your shapefile won't work properly. The really important ones are the DBF, the PRJ, which has the projection. The DBF is the table of attributes, the shape, which is the geometry, and then I think this SHX is the kind of glue that indexes it all together for you. So these are the data sets that we're going to work with. And the first thing we're going to do now that we've got this base map added is add a data set. Actually, let's go ahead and make a bookmark favorite where our data is actually living. If we go to home, that should be my base. And then if I go into downloads here, I should have a folder called QGIS walkthrough. Where are we? The run through. There we go. And so I'm just going to right click and add that as a favorite. And so now I don't have to have all of those folders open. I can just open up this one right here. Now, notice that I also have this project home folder. Conveniently, when you save a QGIS project, it sort of spins this up dynamically. And this is also wherever your QGIS project is saved, that's what this project home is. And conveniently, I've put my data in here. So I'm going to open up the data folder and take a look. And now you see it's a little different, right? We can see the death addresses.csv. We can see the snowmap.png. We can see the study area.shp, but all of those other component files of the SHP file, the shape file, are not there. And so QGIS knows that shape files have to have all of these files, but it gets that out of your way and just shows you what you need to see. And so what we can do, we can double click, or we can right click and add this layer to project, or we can actually just drag this in and drop it into our project. And now we've added this data layer to our project. You can see in our layers panel here, we have 2 layers now. And if I right click on this study area, I can zoom to that layer. And there we are. We're zoomed into this neighborhood that we're going to be looking at for the next hour or so. One problem with this is that I can't see the base map through it. And so the first thing I want to do is enable a new panel and change the symbology of this particular layer. Now, you could do that by double clicking on the layer and bringing up the properties of the layer. You can certainly edit the symbology here, but that's not actually the coolest place to do it because it's not immediate. The coolest place to do it is to go up here to your view and panels and enable your layer styling panel right there. And I'll just open this up a little bit so we can see the whole thing. And this can stay active in your QGIS window. It's a little crowded for me now. I'm used to being on a big monitor, but you can use this on your large monitors and set it up so it's on the sides and you have a nice big map canvas to work with. I'm going to go ahead and click on Simple Fill because it gives me more options to alter the symbology that I'm seeing. And the fill color that I want to use is transparent. I want to be able to see the base map through it. And the stroke color that I want to use something relatively bright. I'm kind of partial to orange, so I'm going to use orange. And then I'm going to thicken up this line to at least 2 points, 2 millimeters, so that I can really see where I'm working here in the base map. And that's it. You saw that those changes were applied on the fly. That's one of the things that I really like about the layer styling panel is that all of your changes to your symbology are applied live, and you can see what's happening without clicking OK and then going back into a properties dialog. Now, I've changed things about my map document now. I've changed the instructions about how to symbolize the study area. I've added layers to it and so on. So I'm going to click Save now so that in case QGIS crashes, which sometimes it does, I can get back to where I was before. All right. So we've added an existing data layer now. What we'd like to do is just investigate some of the navigation tools. Now that we've got data in our map, it makes sense to do things like take the pan tool and pan around our map. This pan tool works just like you would expect it to. It changes the extent of the map without changing the scale. This tool will pan to a selection. We don't have a current selection, so I'll skip that one. The zoom tool works like you would expect it to. It zooms into a particular area of your map. You can also single click to use the zoom tool to zoom into that area. The zoom out tool works a little less intuitively when you drag a box. So what it's going to do now is it's going to take the entire map canvas and it's going to shrink it into the box that I just created. And I can also single click until I get out to the extent that I'm interested in with that. The next tool is the Zoom Full Extent tool. Now, one thing to remember is that we've got a base map data set from Stamen that is global in extent, which means that if I click this, we're going to zoom out to the whole world, right? And that's not optimal for us because what we're really interested in here is the neighborhood that we were working in before. And so I'm going to go ahead and right click on my study area. No, I'm not. I'm going to use the zoom back tool. Notice that I've got this little tool that is now active, and that works just like your browser's back button. So if you zoom back to your previous extent, and then I can zoom back through other extents. Once I zoom back from the latest extent, you'll notice that the next zoom level has become enabled, and that works just like your browser's next button. So I can zoom back forward through those extents. The rest of these we'll save for later. I do want to point out the refresh tool here is often useful as well. All right, so we've got those navigation tools. One other thing I want to point out is down here on this bottom bar of QGIS, there are a number of useful little feedback tools here. One of them is the scale tool. So I can see that I'm working currently at a scale of 1 to about 12,000. If I want to be more precise with that, I can select a precise scale. I can also go in through the interface, the properties of my my project, and I can change these scales. I can use Google Map scales. I can use, there's all sorts of customization that's beyond today's workshop that you can do with that. Another thing I want to point out is something called spatial bookmarks, and these are really useful. So I'm going to right click and zoom to the study area. And then I'm going to show you a different way to enable a panel in QGIS. Before I did it from the view toolbar, but you can also right click in an empty spot in the toolbar, and you can go and enable spatial bookmark manager panel. And that'll come open over here between my browser and my layers panel. And what I want to do is just add a spatial bookmark, and that's the second button here. So I'm going to click on it, and we have a number of parameters we can set. I'm going to call this Soho because that was what they referred to this neighborhood as during this episode. You can create groups of bookmarks. I don't have any currently because this is a clean installation of QGIS, a clean profile. And then you can also set your CRS, and you can save this in one of two places. You can save it at the program level, so it's accessible in all of your projects, or you can save it in this project. And I'm gonna go ahead and save it in just this project. And I'll click save. And now you'll see that I have this bookmark here. And if I go ahead and I click on that zoom to full again, I can either double click or I can use the zoom to bookmark tool here in the bookmark manager to get back directly to that spatial bookmark. Again, that's a change in the project. And so I want to click save to save that change. All right, so now we've got a couple of data sets in QGIS, and we're at the point where it makes sense to maybe, let me check and see if there's any Q&A first. I don't see any. Good, all right, and hopefully David is hanging out, and he should be able to answer some questions. If you put them in the chat or in the Q&A, we can get to those as we go. All right, so let's talk about CRS, coordinate reference systems. And most GIS applications sort of handle these things in the same way. They handle them at two levels. So the first level is at the data set level. And by that, I mean, each of these data sets actually has a coordinate reference system. Let's take a look at our base map first. Our base map, Stamen Toner Light, is coming in as a service from servers at Stamen. And if we look at the source here, we can see that the coordinate reference system that it's using is something called EPSG. And this is sort of a standards board that creates standards and then distributes the data about these coordinate reference system. And it uses codes to get the right coordinate reference system. As you work with GIS data, you will become more and more familiar with a couple of these, WGS 84, and this one in particular, the coordinate reference system code for Web Mercator, this pseudo Mercator projection, which allows you to model the world as a perfect square on a flat surface and then tile it into millions of tiles so that you get these super zooms. So this is the projection of that map service, the base map service that we brought in. Our study area also has a projection. And what I'd like you to notice is that its projection is not the same as the coordinate reference system of the data set we're using as a base map. In this instance, we're using UTM zone 30N, which is appropriate for measuring things. It's a small area so that this projection preserves distance and direction and shape fairly well, except in the higher latitudes maybe. And so we're using UTM zone 30. This is the native projection of that data set that we brought in. We haven't changed it in any way. And so finally, I'm going to go to our project and open its properties. And if we go to the CRS tab in our project, we'll see that our project has a coordinate reference system as well. And currently that coordinate reference system is set to WGS 84 pseudo Mercator. The reason it's set to WGS 84 pseudo Mercator, the same coordinate reference system as our base map, is because we added our base map first. And that is generally how desktop software, GIS software works. When you add a data set, it sort of cannibalizes the coordinate reference system of that data set and takes it as the project data set coordinate reference system. So why is it necessary to have a coordinate reference system at the project level? Well, it wouldn't be if all of your data sets were all in the same projection, but that nearly never happens, right? You see that we're already bringing data sets in that are not in the same coordinate reference system. And so the project coordinate reference system acts as sort of a lingua franca. It is the coordinate reference system that all other data sets that we add to this project will snap to. And what that allows us to do is to co-locate all of these data sets, even though they have different coordinates in the data, co-locate them within this application so that we can at least visualize them. Now, we'll talk about this later. That's not always optimal when you actually want to analyze across data sets. Often tools really do prefer that all of your data sets be in the same coordinate system, and we'll manage that briefly. I'm going to go ahead and cancel out of here because what I want to do is show you how to change the coordinate reference system, at least of your project at this point. Later on, I'll show you how to change the coordinate reference system of a data set. But right now, what we'd like to do is we'd like to put our project into the same coordinate system as our study area. So I'm going to right click on study area and go to layer CRS, coordinate reference system. And here you can see that I have the option to set the project CRS from the layer. I also have the option to set the layer CRS. You don't want to do that unless you know that the coordinate reference system that's currently on the data set is broken and you need to set it to the real coordinate reference system. If what you want to do is change the correct coordinate reference system to a new one, that is an active projection, and we actually need to use a tool for that. We'll do it later. But right now what we want to do is just set the project CRS from this layer. And what you find is that you see that that study area, which was slightly cantilevered a little bit to north based on the coordinate system of the project, has now adjusted itself so that it's oriented north-south. And you'll see that the base map now actually doesn't look quite as good as it did. And that's because the pixels are being warped on the fly and they don't quite line up with one another anymore correctly. Now, for this project, we're going to leave it here. We don't really care about the look of the base map at this point, but eventually, if we wanted to make maps of this, we would want to either find a base map that didn't do that, something like a vector base map, or we would want to project our project back to the same coordinate reference system as our base map, so everything looks nice and clean and not, jagged and pixely. All right, I've made a change again, so we want to click save. All right, so now what I'm going to do is go into, let's see, we've done the CRS. Let's now add the depth addresses. We've got this CSV file that we could add it to our project as is, but it would only add it as a table at this point. And so what we actually want to do is use our data source manager. So I'm going to open the data source manager from the data toolbar up here at the top. And you'll notice it's got this list of data source types. Some of them are formats, some of them are families of formats, sort of types, and so on. And what we're interested in is actually this delimited text, comma delimited or tab delimited, and so on. And you can see that the file format here selected by default is CSV. That's exactly what we want. So I'm going to browse to our CSV that's in our data folder and select that depth address as CSV and open it up. Now, there's a couple more things that we need to do. You can see that we've got a preview of that CSV, and it's got X coord and Y coord. It's got num cases. It's got an address. And here's what we need to do. We need to go into this geometry definition, and we need to verify that QGIS has correctly guessed which are fields that have the X and Y coordinates, and it has. So that's great. But what it has not guessed is what those coordinates are actually in, what coordinate system they're actually in. And in this case, those coordinates are in WGS 84. They're lat long coordinates. We're looking at London here, so it has a very low X X coordinate because it's very close to the Greenwich line and the meridian there. And then we've got this latitude of 51. And so that looks like latitude coordinates. And generally, you can assume outside of the United States that these are WGS 84. Always look at the metadata, but if you can't find it, then it's most of the time it's safe to assume that this data is WGS 84. And you can see the EPSG, this is another one you'll become familiar with, is 4326. Now this tells QGIS that these coordinates are in WGS 84 so that it can place them into our map correctly. It will create a valid projection on this data set so that QGIS knows what the native projection is. And at this point, I should be pretty good to go. I don't think we need to double check any of that. So I'm going to click add, and then I'll close my data manager. And sure enough, we've got this new version of our death addresses here in QGIS. We've got a new layer here in QGIS, and we've got a point for every one of these locations where a death took place in our survey, our area of interest. That's a change. So I'm going to go ahead and click it. And then let's go ahead and we're going to adjust the symbology of this data set now. So you can see I already have my symbology, my layer styling panel open because I used it to adjust the symbology of my study area. And you can see that when I change the highlighted layer in my layers panel, I change the highlighted layer in the layer styling panel. And what I want to do here is I'm going to change from single symbol to graduated. And that's because I've got a variable in this data set that is actually sort of an intensity variable. And so I can create a symbol that's based on, that's a size based on that variable. And that value is the num cases, the number of deaths at each of one of these addresses. I'm going to change the symbol as well. So I can click here and I'm going to select red dot, and maybe I'll bring the opacity of that down to like about 70 and then go back here. So I've changed, that's sort of my template for this particular data set. And then I'm going to turn the legend precision down. And the method that I'm going to use is size. And I think I want these to be from 1 to 50, and probably I want them a little bigger than that. So I'm going to do 10 to 50, and I'm going to change this to map units. My map units, because I'm using UTM, are meters. And what that means is that my symbology is going to, basically it's going to scale as I zoom in and out, and my symbols will stay between 10 meters and 50 meters in size. And so now I'm going to go here to, let's do quantiles and 3 classes. And maybe let's try equal interval. That worked really well, actually. And so now I've got this map that highlights sort of the average number of deaths and then these hot spots of deaths that are occurring around this neighborhood. Most of them centered here at the very center of our area of interest. All right, just a quick bonus, and that's just to show you that QGIS has very sophisticated rendering tools. So if you're familiar at all with packages like GIMP or Inkscape, or even Photoshop and Illustrator, you'll know that the rendering tools are very fine-grained in there, and you can actually use blending modes and things like that. All of those capacities are built into QGIS, which is really handy. There's also some built-in special effects. So I'm going to toggle on draw effects, and I'm just going to give you this a drop shadow just because it looks cool and just to give you an idea of the ability to do that. There we go. And then we'll go back to our styling panel. All right, so I've made changes, and so we'll save that. So now we've got this nice map of the outbreak. We've got some geographic context with our base map. We've got our data visualized based on the value of an attribute in our data table that we've brought in just from a spreadsheet. Could have been an Excel file, a CSV, whatever. And so now we've got this nice map of the outbreak. And what we want to do now is begin to look at the context of this outbreak. And so we need more data for that. let's actually look into the data of this data set first. I'm going to go ahead and zoom to my bookmark here. And we saw a preview of the data set as we were importing it. But if we right click on depth addresses, we can open the attribute table here. And now we can look at this data set as a whole, and not just in a preview. And so we can open all of this up and we can see the addresses, we can see the number of cases. And not only that, but we can begin to play around with the data values. We can sort things descending or ascending and do other things. You know, we can organize the columns differently than they are here if we want to. We can freeze columns and so on within the attribute table. One thing that we can do is get a snapshot of the statistics of a particular variable. And in this data set, the variable that we're really interested in is the number of cases. And the way we do that, since this is a vector data set, is to go up here on the main menu to vector. And I believe it's analysis tools and basic statistics for fields. Yeah, there it is. And so I'll open that up. And because our only real operational layers in the map are depth addresses and study area, QGIS has guessed that depth addresses is the data set that we want to summarize, and that's correct. And we're going to calculate stats on num cases, the field that actually has our values in it. I'm going to go ahead and this is another thing I like about QGIS is it allows you to create temporary files. You don't have to commit to creating a shape file if you want to experiment with settings on the tools and so on. And so I'm going to click run, and this should create a couple of things. It's going to create our little feedback here in the actual Python window, because this is actually running Python in the background. And so we can see all of our variables that we've calculated are available here. But if I close this window as well as this one, I can see that it's also created a visualization. If I click on that link down there, and let me bring this window in, you can see it's created an HTML page as well for us. And so we can see now that, for instance, the total count of addresses in this data set is 322. We've got no nulls in the data set. We've got a sum of 578. So what that means is there were 578 deaths. We have a range of 17, so that means somewhere with a maximum value of 18. So the largest number of deaths at any one address is 18, which is horrifying. And then the smallest number of deaths, of course, because we only have data on locations where there were deaths, is going to be 1, and then we have quartiles and standard deviations and so on. So that's how you get an idea of sort of the statistics of a single field without, casing it and summarizing it in any way. So now we've got an idea of what this outbreak sort of looks like. It's affected some areas more than others. It's particularly nasty in a couple of addresses, and then in general, most households experience a single death in this data set. So I'm going to go ahead and save that. All right. So the next thing we might want to do, and I'm actually going to skip this section, but there's a section in the tutorial that's quite useful for looking for maps. And I'll just say, if you ever want to find an historical map and bring it in already georeferenced, the davidrumsey.com website has hundreds, if not probably hundreds of maps now that are georeferenced already, maybe thousands of maps. In fact, I do think it is thousands. You can go to their site, you can find a map that you're interested in, and in many cases, you can click on an orange button that says View in Georeferencer, and from that page, you can actually download what's called a geotiff. Now, the next thing we're going to do is create a geotiff. So I'm not going to explain to you what a geotiff is at this point, but know that you can download a geotiff and bring it into your QGIS application, or you can connect directly to a web service in the same way that we connected to that web service for our base map. So I'm going to move right along because we're tight on time, and I want to show you how to actually take an image of a map and bring it into QGIS and georeference it yourself. To do that, I'm going to go ahead and turn off my depth addresses because I'd like a nice clean base map to work from. And what I need to do now is go to the raster tools on the main menu and turn on my georeferencer. I'm going to bring it down here so you can see it. This is a plugin. It's one of the default plugins. So you notice I didn't have to install it. It's installed by default in QGIS. And the first thing I need to do is give it something to work with. And so we'll go to our, let's see, workshop here. And in data, I should have a snowmap.png. So I'll open that up. And if I'm lucky, there we go. It opens up that PNG here in the interface. Now, this is still just a dumb image, right? And so now what I need to do is I need to tell QGIS what the pixel coordinates in this raster data set. Remember, it's made of pixels, and those pixels are on an XY grid. I need to tell it what the pixel locations correspond with in the real world. That is, if I have a pixel coordinate pair, what's the lat-long coordinate pair that it corresponds to? Before I do that, I need to set up the job a little bit. So I'm going to open up the transformation settings. And the transformation type I'm going to use is a polynomial 1. And what this does, it's referred to as an affine transformation. Because I'm working in a very small area, which is referred to as a large scale map, because the features appear very large and the fraction of the scale is very large. In these large scale maps, generally a first order polynomial is sufficient. And what a first order polynomial will do is it will take your ground control points, which is what we're about to create, and it will move your map, it will resize your map, it will rotate your map, and it will skew your map, but it won't do any more than that. And what that does is it keeps straight lines straight. It does the best job it can in closing the gaps between your ground control points without doing what's called rubber sheeting. That is, warping the map in a way that's not uniform across the entire map. A second order polynomial would do that, but what you would end up with is slightly curved streets in some cases, depending on the distortion of your map. All right, resampling method, we'll use nearest neighbor. What that will do is simply when it recalculates the raster data set, it's going to calculate based on the actual values of our raster data rather than interpolating them and creating sort of a grayscale. That would create sort of a haziness in the image. And it wants to know what we want to target, what CRS, coordinate reference system, we want to target. We're going to use the project coordinate reference system because that's the coordinate reference system that we want to work with in general with our other data sets. Here, it's going to put the TIFF, the resulting data set, into the same folder that, that your source data is coming from. Compression I don't normally use because it can create artifacts in the image, and I like nice, pretty images. Give me 1 second. Pardon me. We do want to save the ground control points as we export. That'll give us more information about how this particular data set was georeferenced. And we do want to use 0 for transparency. Otherwise, we're going to get this these weird black triangles on the sides of our georeferenced map. So that should be it for settings at that point, I believe. And so we'll click OK, and then bring our georeferencer back forward. So at this point, I'm ready to begin adding reference points. So I'm going to zoom in first to this area right here. And I'm using a 2-finger swipe with my Mac trackpad to zoom in. And I'm going to place a point right there on the corner of that Soho Square feature. And now I get a pop-up, and the pop-up asks me, do you want to put in the X and Y coordinates manually? Gosh, no, I don't want to do that. I want to go pick them from my map canvas because I've got another data set there that I can use as a reference. So I'm going to click that, and then I'm going to zoom right into Soho Square in my map canvas. And I'm going to click right on the edge, that corner, same corner, and then it brings me back to the georeferencer. This looks good, so I'll click OK, and I get a dot there. Now, I'm going to zoom out so that I can see my image again, and then I'm going to zoom into Piccadilly. I think this is, no, it's Regent Circus. Piccadilly's down further south. And I'm going to place another coordinate right there, ground control point, and then go back to my map canvas and zoom out of my map canvas and zoom into the same location here. And hopefully we'll get to see, let's see, there it is. This is it, right? Ooh, it may not be. That may be a bad point. Let me go back here and see if I can get it to zoom out the way I want. Nope, that actually is it. All right, excellent. All right, now I'm going to zoom out. And if you zoom out on a point up here, then you'll see that it kind of pulls the map one way and you can get to the bottom of it and then zoom in. And here I like to go for, let's see, let's do Burlington and Clifford. And hopefully we'll find that in our map canvas. There's Burlington. And let's see, can we get that label to come in? Trying to see the label for this. Let me go ahead and bring in a handy little Google Labels feature and just bring that up. Another reason why that is really useful. So there's Burlington, and it doesn't, I think it's this one right here. So we'll go for it. This is probably going to be terrible. Let's see what our residual is. And that might be a pretty big residual. I might have to replace that point. We'll see in a second. And so now I'll zoom out and we'll get right in here. Find it good. Oxenden and Coventry right there. That's an easy one. And from map canvas, let's turn off our Google labels. There is, I think it's actually that right there. Okay. And residual in pixels, that's not too bad. That's actually worse than we want. So I'm going to take the number 2 one out. That's the one that we created before. I'm going to uncheck it so that it doesn't get used and place a new one. Let's see. That one. And here we go, Albemarle and Grafton. I know I can find that. So often when you have a map that's very large, you're going to place far more points than this and to get good results. And that may be because the map is very old and you need to allow for some distortions. I once georeferenced a map of New York in the 1950s, and I had to use about 100 ground control points to do it. This is going to be good enough for today. So now we've got these ground control points placed. And what I need to do now is simply click the play button to start georeferencing. And that's going to export this data to a new map layer. And so that's been successful. I should be able to close this. And I didn't check add it to the map by default. So let's see, there it is in my browser. And if I add that to my project, I should see it there. Zoom to that layer and notice that the it's kind of terrible, the symbology. So let's try stretching it a little bit and see if we can figure that out. So it's a better one. Ooh, that's just terrible. Why did it do that? Take these lower ones out. All right, so here's where that extra data set comes in handy. I must have missed a setting. So I'm going to come in here and I'm actually going to do the thing that I told you could do. And I'll just remove this previous one. All right, so now we have this map that we've created, and you can see that I didn't use the no data setting there when I created it. We've got this map that we can zoom into, and we can see, most importantly, where all of the water pumps are, and that's what we're going to be working on now in the rest of this. And so I'm going to click save because I've made changes. And what we're going to do now is we need to create a shapefile, an empty shapefile to put our data into. And so I'm going to go here to layer and create layer, new shapefile. And you do need to browse. Actually, if you just put the name of the shapefile, it can sometimes give an error, or sometimes it just puts it in a really weird place that you can never find. And here is our workshop run through. We'll put this in data. We're going to call this water pumps. We'll save that. And the geometry type is going to be a point. System encoding should be fine. WGS 84, this is just going to be pure lat long coordinates. This is actually an archival coordinate system. And so it's the preferred coordinate system when you're creating data sets. I usually suggest people use WGS 84 to create their data sets. And so what we'll have to do when we want to use this is project it to a projected coordinate system in a few minutes. Now, I do want to add a field. We're going to call that field label, and that's where we're going to put the name of the street that each of these water pumps is on. And then we'll click that add to fields list to add it to our fields list. And that should be all we need to do. So let's click OK. And now you'll see that we should have a water pumps data set here. I'll drag it up to the top. And it has a symbology, but it has no data. So you don't see it in your map canvas here. Let's go ahead and change its symbology. And I'm going to change it to this red dot. And I'm going to increase the size to about, let's say like 7. That might be too much. Let's do 6. And I'm going to change the color to a more appropriate, nice blue for water. Okay. And so you can see that's reflected down here. It's not yet reflected in the map because we don't have any data in the map, in the layer. So now we're actually ready to put data into the layer. And the way we do that is we have to crack open the shapefile. And so to crack open the shapefile, we right click in the layers panel and we'll toggle the editing. And you can see that suddenly my editing toolbar up here at the top has become active. And so what I want to do is I want to add point features. So I'm just going to get the add point feature tool, and I'm going to zoom in here and I'm going to start adding these features. And this one, this water pump is in Oxford Market. So and as I add them, I'll just put the name in. This one's at Marlborough Mews. Got another one here that's Carnaby Street. There should be, and I'm using my arrow keys here to easily move through this without changing the edit tool. There should be 13 of these. We'll call this one Castle Street, mainly because that's the street that I can read there. Burners. And so we're just building up this data set, adding features and creating their attributes as we go. Newman. Zoom out here and find the rest of these. Let's see, we'll just get right down in here into the world famous Broad Street pump. You know, if you ever go to London and go to this location where the Broad Street pump is, there's now a pub there called the John Snow Pub. Nice little pub. You can visit it, and you can actually walk down into the basement where the famous cholera outbreak began in the cistern down there. the restroom is where the cisterns, the cesspool was. And this one is, looks like Rupert. And so I'm just zooming in and out to find all of these. We'll call this Tischborn. And so on. Let's see, which ones am I missing? I think I've got a couple right there. This one's, let's call this one Brewer since I can't see it. And then I saw one over here. Let me see if I can pull the map that way. Yeah, there we go. We've got the Warwick pump. All right, so let me zoom to my layer here. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've got a couple more pumps. I think there's one right there. It's Vico. And let's see, let's zoom to study area. And compare, I think there's the last one right there. Even I have trouble finding these things sometimes. And I can tell you, I've digitized these 100 times. I think this is on King Street. All right, there we go. So now we zoomed a layer, we've got this layer that has not only the locations of the water pumps, but if we open up its attribute table, we should find that it's got labels with the streets that each of those are on, right? So great. And now what we'll do is we'll just toggle off our editing, and yes, we'll save that. And so now we've got this nice shapefile that has all the data that we're interested in. Go ahead and save that. And let's see, let's apply labels really quickly. And we're going to use single labels based upon our label field. And you'll see that those labels start to come in. They're not terribly visible. So we'll bump those up to about 15. And then finally, I like to put a buffer. So we'll do a white buffer on those. It'll kind of separate them from the background, maybe make it just a tiny bit bigger. And that cleans that up so you can actually read those labels. All right, so that's some changes we've made there. All right. Now, we created this data set, remember, I said in WGS 84. We've got other data sets that we're working with, in particular, this study area data set that we know is in UTM coordinate system. And often the processing tools want data sets that you're using together in a particular tool to be in the same coordinate system. So what I want to do now is I want to project my water pumps data to a new coordinate system. And the easiest way to do that is to simply export this data set as a new data set. And as you do, change the coordinate system. I'm going to export this to an esri shapefile, and I'll call it, let's see, we'll call it water pumps and projected. And then the projection that I want to change to is the coordinate system of my project, the UTM coordinate system. The rest of all of this is doesn't need to be changed, and all we're doing is changing the coordinate system of this data set. So if I click OK, I get a new version of my data set that comes in, and it's fairly ugly. You can't see it too well because I've got my old data set there. If I turn it off, you'll see I've just got these little points. So here's another tip and trick, something that I really like about QGIS. If I highlight that water pumps in my layers tab there, and I go to styles, I can copy the entire style, including the labels of that layer, and I can apply it to my new layer. Because the only thing that is different about that data set is the projection. It uses the same field for the labels. It uses the same symbology and so on. And now I can remove this original data set and just keep my projected water pumps. So now my water pumps and my study area data set are in the same projection. And now we'll find out why they're in the same projection. Let me click save. You'll find that I habitually click save all the time, often right after I've clicked save, because I've been conditioned because I've had so many projects. I've lost so many hours through a crash in that way. All right, so the next thing we want to do with our data is we want to actually assign each of our depth addresses, and I'll turn those on so you can see them. We want to assign each of our depth addresses to a particular water pump based on proximity to that water pump. And the method I'm going to use, there are a couple of methods we could use, but I'm going to use a very visual method, and it's called voronoi mapping. And we're going to create Thesan polygons. The tool is called voronoi. But what we'll do is we'll create polygons around each of these water pumps that are created in such a way that all of the space in the polygon that is created by the Carnaby Street water pump will be nearest Carnaby Street, and so on. So the space around Oxford Market will be nearest Oxford Market, and we'll create a polygon around this Broad Street pump within which all of the space is nearest the Broad Street pump. That's going to be a processing tool. So this is going to be our first sort of geo process that we're going to run. And so we're going to go to the processing toolbox and we're going to search for voronoi. And there are a couple of tools. I actually like the voronoi tool the best, but you see that it's under this group called GRASS. GRASS is another GIS application, and QGIS provides sort of a user interface into GRASS. But sometimes when they update QGIS, it gets a little breaky. I'm going to try using voronoi because I do prefer it. My input points layer is going to be my depth water pumps projected. And then my advanced parameters, let me just open this up so you can see it. I'm going to set the extent that I want to use. I'm going to calculate that from my study area layer. And here is where, if this works, if the GRASS tools are working properly, these two need to be in the same coordinate system. You can see that they are. The rest of this, I believe, can be left as is. And I'm actually going to save this actually. So we're going to save this to a file, and we're going to call this voronoi.shp. Change this to shapefile, save it, and there we go. That looks all good. And I'm going to cross my fingers. You wouldn't believe how useful it is to cross your fingers. Sometimes the difference between it working the second time and not working is that you cross your fingers the second time. I'm going to click run, and we're going to pray for no red text. Oh, that's unfortunate. That means it failed. All right, so what we'll do is just bring this back. These are all kinds of probably Python issues that have been baked into the new LTR. But fortunately, there's a lot of tools that are baked into QGIS that allow us to do this as well. So I'll close this. And you'll notice that under the QGIS group with the QGIS logo, there's this voronoi polygons tool. Now, it doesn't provide as much control over the area that you're creating polygons over as I like, but it'll do. So we're going to select water pumps. We're going to give it a buffer region of 50%, and we're going to call this voronoi polygon data set just voronoi. I don't think the other one actually created a data set, so it's not necessary to override it. Open the output. There we go. We're going to run it, and yay! Look what we got here. All right, so if I turn off my depth addresses, what you see is something quite similar to what you saw probably the first time you looked in a microscope in biology class at onion skin cells, right? So you've got these central points. These are the generating points of these voronoi Thesan polygons. And around them, you've got a polygon. So within this polygon, everything is nearest the Broad Street pump. That's really handy because the next thing we're going to do is a spatial join. We're going to, conceptually, we're going to push our depth addresses through this voronoi polygon data set so that the attributes of the voronoi polygon data set stick to our depth addresses. And what that's going to do is it's going to transfer this label field, which was transferred over from the water pumps when we created our voronoi. It's going to transfer that to our depth addresses, which is going to become very useful. All right, let's go ahead and do that. And I would normally change the symbology here, but I'm just going to move right along. The next thing we want to do is actually, let's see, is everything in the right coordinate system? I'm going to go ahead and export. I remember that my depth addresses came in as WGS84. So I'm going to go ahead and export this layer as well. So I'm going to save it as an esri shapefile. I'm going to call it just depths. How about depths projected? Sounds like an Agatha Christie novel. There we go. And I'm going to change this to the project CRS so that it projects the data as I export it, and just click OK. And I get a new version. If I wanted to, I could copy and paste the style in, but really I just need this for working with the data, doing some data carpentry. So the next thing we want to do is go to Vector Data Management Tools, and we're going to join attributes by location. And so you always start these tools by selecting the data set that you want to augment. And in this case, depths projected is in fact the data set we want to augment. We want to add the attributes of our voronoi polygons to it. So we'll select voronoi as the join layer. Intersection is the correct geometric predicate here, so that we're only going to join the attributes of the voronoi polygon to the point if the point is within that polygon. You can see other ones here that would be very useful. So within, overlaps, equals, touches. You can also create nearest spatial joins in other ways, and so on. We're going to leave this empty to transfer all of the fields. The join type that we want is in fact a one-to-one join type, and we want to export this to a new data set. So we'll save this as depths, and we're going to save it as a shapefile. In general, I like to use shapefiles, well, I like to use GeoJSON a lot too, but shapefiles have the advantage of having metadata in the file itself about the type of attribute that is contained with each of the columns. GeoJSON doesn't do that. So it treats basically everything as text if it's in quote marks as a property in the GeoJSON file. And that can cause weirdnesses with some of the other tools that we're about to use. I think that's it. And at this point, I'm going to cross my fingers and run the tool and close it. And hopefully we have this new depths data set. And if we open its attributes table, we'll see, yes, we've got num cases there. We've got all of the original data of our depths data set, but now we also have the water pump that each of these depth addresses is nearest because it's within the voronoi polygon of that particular water pump, right? So now we can do some interesting things. Remember at the beginning when we did that summary stat on num cases, now what we can do is we can summarize the number of cases based on which water pump they're nearest. And that's going to be really useful. So let's go and do that right now. That is actually another plugin. And so this is a plugin called Group Stats. It's incredibly useful. So we'll go back in here to our plugins and search for group. There it is right there, Group Stats, and we'll install that plugin. Plugins in QGIS are very similar to the Art Toolbox tools in ArcMap. You'll find that most of the functionality, a lot of the functionality is built into QGIS, but when you want to start doing esoteric things, sometimes, like classifying satellite imagery and things of that sort, you'll find that that's going to be a plugin that you bring in that someone's written. Someone's turned their Python code into a plugin for QGIS, and there are thousands of them, and many of them are incredibly useful. So now we've added group stats. We're going to go here to vector, and we'll open up our group stats tool. And we're going to set this to our new data set called depths, which has all of the data from the voronoi polygons, as well as our depth address data. So our columns that we want to calculate are going to be those summaries of the data. So average, count, max, median, let's add, a couple of these standard deviations and so on. Our rows are going to be the water pump names, which are contained in the label field, right? And then the value that we're summarizing is going to be num cases. So we'll calculate, drag that in here. I love group stats because it's just a nice, easy sort of drag and drop calculation. And now if I click calculate, we see we get this nice little table, and it's even sortable. So if I click on it, I can sort on the average, And I can see that Broad Street comes in just behind Marlborough Mews. But if we go to count, of course, Broad Street and Max and the medians, this Marlborough Mews comes in ahead of Broad Street because it has such a small number of records probably. And then we can see standard deviation. So we get this nice little table that summarizes statistically each of our sets of death addresses based on proximity to the water pump that they're nearest. Now, the final thing I'll show you with this group stats is that you can go up here to data and you can save all of that information to a CSV file called deaths summarized. There you go. And if we go back to our Finder, we should find that we have, there it is right there. And we can open this up in Excel or numbers or whatever we use for spreadsheets. Okay, so we're done with group stats. So we'll go ahead and close that. And finally, let's see, we've got a couple of basic measures of spatial central tendency that I want to go through with you while we've got 10 minutes left. Just perfect. That's great. The first one and the most common is the spatial mean, and that's an easy one to calculate. You can actually calculate it in Excel quite as easily because it's just the x coordinates and the y coordinates, each of those columns averaged, and then you take those two averages and treat them as a coordinate pair, and that coordinate pair is the point at which your distribution of points sort of balances. Think of it this way. Think of it as if we took our snow map here and we printed it on a big piece of cardboard. And then we put a quarter at each death address and found the balance point of that map. That's exactly what we're doing here. We're finding that kind of balance point. And in a minute, I'll show you a different flavor of that as well. But let's go up here. I think this one is actually geometry tools, and is it in a spatial mean? Sometimes they put these things in the not. There we go, mean coordinates. And deaths is exactly what we want to use. We want to find the spatial mean of this entire distribution of points. And I'm not going to weight it or use the unique ID field. And in fact, I'm just going to send it to a temporary file just to show you how that works. And so now we've got this new data set. I'll close that. It's right here. I can go to layer styling, and I'm going to change this to a nice big little explosion here that we can see. And if I zoom into that a little bit, we'll see there is the spatial mean of that distribution of all of the deaths in this data set, right? And you can see that it's right next to this Broad Street pump, right? All right, so the next thing, let's run the tool again, actually. And so we'll go back to, I believe, if we go to the processing toolbox, it'll show up here. No, and we'll just go back here. Analysis mean coordinates, and we're going to use our deaths, and this time we're going to use a weight field of num cases. Now, same analogy, we've printed our map on a big square piece of cardboard. This time, instead of a single quarter at each address, we're going to put a stack of quarters, and that stack of quarters is going to represent the number of deaths at each address, the num cases field, right? And so we'll click run on that one. And we'll go ahead and give it a nice explosion there, and we'll make it yellow so we can see it. And you can see that that weighted spatial mean has now actually moved even closer to the Broad Street pump. Not much. This is a tight distribution of points, but it has in fact moved closer to the Broad Street pump. Finally, let's go back to our mean coordinate tool. And we will use deaths again, we'll weight it again, and now we're going to use a unique ID field. And the unique ID field we're going to use is label. And this actually outputs something interesting. I'm just going to click run and close it, and we'll just go ahead and get this worked out right now. And we'll make it what's colorful enough to see. There we go. How about some pink? Yeah. All right. And now if I zoom out, you can see that Broad Street pump spatial mean there, and And because it's only using, so by using the label as the unique identifier, what we've done is essentially cased our spatial mean. And so this is the spatial mean of the distribution of points that is nearest the Broad Street pump, weighted. If we zoom out, we can see that we've got spatial means, and this works really nicely when we've got our voronoi turned on. We've got spatial means of all of these other distributions of points as well. And what you see is that in every case, the spatial mean of the distribution of points is actually pulled towards the Broad Street pump. And so the Broad Street pump is sort of acting as this attractor within this distribution of points. All right, so let's go ahead and click save. And I've got one thing to show you. And let's see, we'll do standard distance really quickly. So here, and that's going to be in a set of tools called the point pattern analysis tools. And these are in something called Saga. This is another desktop GIS application that QGIS acts as an interface to. And you'll notice that Saga, the newest version of Saga, is not fully supported by QGIS. So we'll cross our fingers on this one because this may or may not give us the results that we're interested in. We're going to feed it our depth data set. And we'll just leave everything as temporaries. And so what this is going to calculate for us is another mean center, a standard distance, which we'll talk about in just a second, and a bounding box. So we'll just run that. Looks promising. There we go. All right, excellent news. So what we've got is, first of all, it puts our mean center underneath all of this, which is not optimal, but there, if we turn off our pump, what we end up with is a mean center right there. And that's the one that was calculated by this tool, and then a standard distance. The standard distance is actually the polygon within which 67 point whatever it is for one SD, 67% of our data, roughly 68% of our data is within this polygon. It is the radius, the standard distance is the radius around the spatial mean that contains one standard deviation of our data. Now, in this case, because we didn't weight it, it is just it is one standard deviation of the addresses, not the depths. And then 2 would be, like 2 standard deviations and so on. So that's useful. And then often a bounding box. So it calculates this bounding box as well. And this is just a minimum bounding box for this entire array of coordinates, which can often also be useful. All right. Did I mention this is not a cartography workshop? Cartography workshop comes later. David Medeiros, who works with me at the Stanford Geospatial Center, has got a couple of cartography workshops. You'll find links to those at the bottom of the tutorial here. And I would suggest you go to those. I'm not going to teach anything beyond, where you can find the layer styling here. The last thing I want to do is create a hotspot map. And this is actually something called kernel density. There are a couple of versions of the tool. I actually like the other one better, but I think this one's probably more stable, so we'll give it a shot. This is essentially heat mapping. It's going to create a heat map of our depths. And the radius that we're going to use is 50 meters. And so what this does is it divides our area of interest up into pixels, and it starts at 1 pixel, then it looks for 50 meters for all of the depth addresses within 50 meters of that pixel. And it's going to use the num cases to calculate the value of that particular pixel. And it's going to create what essentially is a topography of the outbreak, so that we'll be able to see hotspots as if they were peaks in an elevation model. Let's see, the weight that we want to use is num cases. The rest of this, I generally just use the defaults. And so now I'll cross my fingers and click run. And yes, lovely. Look at that. All right, so let's turn off my voronoi. And so we can see that And in fact, if we go into layer styling, just to show you how to style a raster data set, this is a single band raster data set, and I'm going to use a linear interpolation. I like to use this magma. It's nice and hazardous looking, and yeah, there we go. That's about right. And so now what we've created is this interpolation of every pixel within 50 meters of a data point, and we've interpolated it so that it's sort of this undulating topographic data set. And in fact, if we wanted to, we could actually export this to a three-dimensional application and look and drape the snow map on top of it, do all kinds of fancy things. But what's important to note is that the hotspot in this map is actually sitting right on top of our water pumps, of course, because the water pumps are the culprit. And you can see that, in fact, it is the Broad Street pump, which John Snow, of course, found. The Broad Street pump was the pump that had, in fact, been contaminated by a cholera outbreak that had begun at 40 Broad Street. And this location right here, and they had dumped the soiled night sheets and the buckets, the soil buckets, into the cesspool. That cesspool had leaked into the Broad Street well, and that's when one of the most virulent cholera outbreaks in Soho in London history began. For over the course of about 2 weeks, about 10% of the population of this neighborhood died, and people just fled. One of the things that was really revolutionary was that John Snow went into this neighborhood and interviewed. He did data collection on the outbreak. He tracked down every death. He tracked down not only how many people died at each address, but sex, age, occupation. There's all kinds of fantastic data that's actually still trapped in John Snow's notes in the appendix of his final report on the mode of transmission of cholera, which is about this outbreak and other outbreaks that he studied, and you can find in the Stanford collections and elsewhere. All right, that is it for the workshop this week. I do want to pull my QGIS or my GitHub tutorial down. You can see that everything that we did is in this GitHub tutorial. It's all that I went through. There's actually a little more in there. And then finally, right here at the end, you'll see that I've added 2 links. And these are to QGIS cartography workshops. One of them is a basic cartography workshop that David Medeiros has put together. It's really fantastic. You've got a set of slides here. You've got a video walkthrough, and then you've got the download here for the materials to open up and work through the workshop on your own. This is the basics of creating layouts and symbologies and other things in QGIS, and is sort of the equivalent. It's a great actually, it's much better than this workshop, but it's the equivalent for creating beautiful cartography in QGIS of what you just went through in terms of doing spatial data carpentry in QGIS.